Hello, good morning, and welcome to the Strategic Innovation Fund's Round 2 Show and Tells, where today we'll be hearing from a collection of projects looking at making the system smart, safer, and more flexible. My name is Manu Ravishankar. I'm an innovation lead. I work for Innovate UK in the Strategic Innovation Fund, and I'll be kind of moderating and running the session today. If you can move on to the next slide, please. So we've got a great collection of projects today, and I'm just going to run through a little bit on kind of what they're going to be covering, just to set the scene and then kind of hand over to them. Each project will have 15 minutes, and then we'll have a chance to do Q&A, so to make sure you have your questions ready. So first of all, we'll be starting with Shifting Currents, which is essentially looking at the synergies between the water companies and the energy system in terms of unlocking the kind of potential flexibility there, and is looking to leverage some of the large loads in things like water pumping to deliver, I guess, a more stable and flexible power system. And then we move on to diversified flexible queue management, which really is looking at leveraging both the load side flexibility, but also looking at the inherent diversity in the supply loads to actually go beyond opening up just flexibility for system balancing, but actually helping up to free up network capacity so that we can connect assets faster to the energy system and open up headroom, which all of us know are a really critical issue. So that's quite exciting to see. And then we move to Power Block, which is really looking at analyzing and characterizing commercial buildings to enable them to provide flexibility, but at the same time ensuring the occupant comfort is kept at the center of the proposition. And then we'll be taking a 15 minutes break, and then coming back and looking at the hybrid storage systems project, which really is taking us from the power system into the gas system, where essentially it's looking at solid state hydrogen storage to decouple production and use to enable primarily the gas turbines, which are situated in the compression sites, to decarbonize and use hydrogen, but also, I guess, enable wider supply and demand matching in the system. So that essentially forms the first collection of flexibility projects. And then really we move to projects looking to understand and support future system stability. First of which we'll be looking at Insight, which is looking at how a future power system that might be, majority inverter-based resources really will impact system stability and oscillations. It is looking to kind of better understand it so that we can simulate it, we can monitor it with a view to ultimately developing a control system that helps us to manage these potentially impactful oscillations. And finally, and quite fittingly, we'll probably end with Blade, which is really looking at black start, which is when the whole system essentially is partially or fully shut down and really needs to be recovered. And Blade is looking at novel ways, particularly via offshore wind farms, to potentially restore the energy system in a more cost-effective and low-carbon way. So as you can see, we have a fascinating and critical collection of projects developing ideas that could underpin the future energy system to make it smart, stable, and flexible. And just a quick note on the show and tells. These show and tells are a critical part of the Strategic Innovation Fund. And actually, it's a critical part of, broadly UK PLC's wider effort on energy innovation. This gives us an opportunity for projects to talk about their key findings, to influence other people's thinking. It helps to spawn new ideas. And of course, it lets them be challenged by the wisdom of all of you asking questions. So I guess in that spirit, please do introduce yourself on the chat. You never know. This might be the day you make lifelong friendships over, people for the love of system stability, or actually you might find the next project partner for your next project. Make sure you write down your questions in the Q&A as the projects are presenting. I will pick them up at the end of each presentation and put them to the projects. This is a fascinating set of projects, and I myself have a lot of questions, but I generally have a lot of opportunities to ask these projects these questions. So, make sure you use this opportunity and put the questions to the projects. So I think that's enough for me. Without further ado, can I now hand over to Nick Devine and Gary Swandles to talk about the Shifting Currents project. Nick, over to you.
Hi, yes, good morning, everybody. So yes, my name is Nick Devine. I'm an innovation engineer with National Grid Electric Distribution, and I'll be introducing the Shifting Currents project before handing over to Gary Swandles from Smart Grid Consultancy to talk about what we did and what we learned. So if we can move on to the next slide, please. So quick agenda today. So I'll be taking items 1 and 2, doing the introductions and the problem statement for what we were trying to address. And then Gary will carry it through to review of what we did over the project and then looking ahead to what we want to do next. Next slide, please. And again, please. So the project team, so we had National Grid Electricity Distribution as the network lead, was supported by UK Power Networks in this endeavour as well, with a variety of water companies involved, so Anglian Water and Severn Trent, and have had our historic relationship from South West Water as well. And Smart Grid Consultancy were delivering the main volume of work on the project. Next slide, please. So onto the problem statement. So Shifting Currents is actually a follow-on from a Network Innovation Allowance project. So that we did preparatory work that brought us into SIF. So the Flowers project was a sort of cross-utility challenge to identify where the operations of each utility, electricity and water, could be more sympathetic to the other, and sort of unlock shared net zero benefits through the flexible operations of water networks. So we sort of calculated how this could be possible with a number of assumptions and identified use cases and methods largely around the timing of pumping of water. So we're talking about both drinking water and wastewater here, and how the timing and really the latency in that, in terms of, for example, pumping drinking water ahead of use could be used to shift electrical demand in ways that are sympathetic to the electric water network, and so unlock net zero benefits for both electricity and water companies who largely share the same customer base. We established some base principles from Flowers, which was just a feasibility study, but we needed to test their replicability across the country and sort of demonstrate the value with a real world trial. So this is why we aimed the project at the Strategic Innovation Fund. So to talk about what we actually did in this project, I'll hand over to Gary now.
Thank you, and good morning. Can we skip a couple of slides to the art of the possible? So looking back at, we had a slight advantage over many of the other projects in SIF, in that this is a follow-on to an NIA project where we were challenged with establishing the art of the possible. That was done through engagement with South West Water and understanding many of the challenges that they have, some of them based around net zero and the difficulty that they will have in achieving net zero without some dramatic change to the way in which they operate. So in order to investigate that more fully, we looked at across the nature of their business. It clearly has very high demands on the electricity network, and as well as that, both being regulated businesses and utilities, there is I'd be cautious to say it, but there's almost a sort of socialist approach to the benefits that can be achieved from working with across the whole utility system. Then advantages and benefits can be achieved, which are then received by all customers, which in respect of these two utilities reflects most households and businesses across the country. So looking at the art of the possible, we did a desktop study, and what we did is we looked at quite a number of their sites, both in the clean water and in the wastewater, the streams, and also looked at potential of future electrical loads, such as EV charging, because there will be a big drive within the different water authorities to move their electricity, move their vehicle movements onto electrical systems as well. And that in itself will undoubtedly have an impact on the distribution networks. So looking at this, we gathered data from many of the sites that they have and investigated the latency that they have and looked at it in accordance with the flexibility services that are already being run by the distribution networks. However, we were very conscious of the fact that flexibility programs have been around for quite some time now, yet in spite of the potential that the water companies have, there's a very limited amount of that flexibility actually operates within any of the existing programs. So rather than just looking at the identification of flexibility, probably the more disruptive element of the previous trial, and also what we're looking at Shifting Currents, is identifying the potential of alternative incentives in order to encourage the water companies to work within the flexibility requirements the electricity networks have. So we've already developed quite a number of use cases, 16 in total, which capture the flexibility that's on offer within the different the different industrial processes they have, as well as the potential future consumption profiles from electric vehicles, etc. Can I skip forward a slide, please? So in the process, we looked at taking the outputs that we already had with the use cases and establishing, first of all, whether those were localized to South West Water only, or whether those can be achieved right across the water networks. And probably some of the key factors are whether the industrial processes are different, driven by the topography. South West Water is clearly very different from some other areas. If we look, for example, over to Anglian Water in the east of the country, the land is far flatter. So the processes of treatment and pumping, etc., do have significant differences. But going through the process within Discovery, we took these use cases and captured data from quite a number of the for quite a number of the sites across all of the partners we're looking at, and carried out a similar technical assessment in order to establish whether the art of the possible and what we were hoping to identify within the NIA trials actually transpire through to a wider geography and a wider area of the market. So coupled with that and identifying that indeed we've not seen anything conflicting with the assumptions that were made from the previous project Flowers, and it's worth noting that the closed down reports are all published from Flowers. So if you're interested in finding out more about the detail of the industrial processes that we're looking at and the latency that has been identified, those can be read in the Flowers outputs. However, looking at the processes that are there, they're very similar, albeit in different volumes and depending on the topography. But looking at the technical assessments, that would determine that there is flexibility there. But realistically, the biggest push that we're going to have is looking at the alternative mechanisms of rewards. And in those cases, what we're looking at is the potential of helping the water industry get more renewables online, closing the gaps between the control rooms, which largely operate independently of each other, but with a greater understanding of the challenges, is actually shifting the latency into periods where there's flexibility challenges for the electricity networks. But rather than pushing that into a system where it can be relatively transient, and there's the opportunities to generate income are sometimes not long-term enough for the way that the water industry itself does its budgeting. So looking at alternative mechanisms that would, first of all, help them in acquiring more renewable generation, which in turn would help with their net zero targets. Can we move on to the next slide, please? And I'll just touch on project conditions. Oh, so I'm sorry, if we could, I've already talked through that process. If we could go to the, yes, so yeah, if we, from the Flowers project, there is quite a significant value that we identified. We've tried to extrapolate that out as to the potential that may exist across the country as a whole. Within Flowers, we identified anywhere between 18 to 34 megawatts. The variation is due to seasonality and also some level of investment that would be required in order to release that capacity. But based on them only having 2 million customers and 18 to 34 megawatts of capacity, if that's then extrapolated out to the UK population, and I appreciate for the discovery phase, this is a very rough method of extrapolating out the benefits. But what we could be looking at is anything from half a gigawatt to a gigawatt of flexibility on offer from the water industry as a whole. Using the figures that NGED themselves have for procuring electricity, that could be as much as a £5 million benefit to the electricity distribution as a whole per annum. If we could skip to the next slide, please. So in terms of moving forward and within going from discovery to alpha, realistically what we're looking to do is within discovery we've confirmed that the practical approach is the same, but as yet we've only really done this at a desktop level. So if we're moving through into the alpha phase, what we're looking to do is identify the best sites across the partners that we're working with, and from within that is actually carry out some full operational trials on each of the different site types, be it wastewater or freshwater, or drinking water, I should say, and actually establish whether the desktop analysis and the assumptions that are made therein can actually be achieved in proper operational outputs. And that would also include starting to look at the methods by which communications would take place between the control centres, looking to the regulators to engage and discuss different mechanisms and different alternatives for incentivizing that take them outside of the current the markets that are developing. And then also, if we're looking to encourage the behavioural change at a local level, is also to understand how the carbon is calculated, and moving away from using average carbon from the total consumption of electricity as a whole, and identifying the actual localized carbon impact of shifting around the load profiles in order that they can achieve better efficiencies for within the networks. I recognize that I'm running out of time here, so if we could skip forward to the slide around project conditions, that's the one. So we were set project conditions at the start. There was three main project conditions that we needed to make sure that we were in support of, and there was no significant conflicts. The first was a review with the electricity market, the REMA review that's taking place, and within that, actually, there was, not only did we find that there was no conflicts, but there was actually a number of positive coordination with it. Moving on to looking at the other SIF projects, there was a couple that were flagged as could impact because of their interests within the water industry as well. Most specifically, the next gen electrolysis, which again could be looking at introducing some new but highly latent loads within the water industry. So if both projects were to go forward, those connections have been made and the coordination will be done. And then finally, to engage with Ofwat, particularly around their innovation teams, to flag this as a potential area of investigation and innovation, and ensure that they were happy and on board. And indeed, they have stated their interest, and if the project goes forward, would be brought on board as a stakeholder. I think that's probably, as I'm tipping over into 14 minutes, probably a good point to stop for questions, Manu.
Thanks, Gary. I mean, you did start a little bit early, but you finished, I think, a little ahead of time. That's no problem at all. And maybe through the discussion, you can bring out any points that you may have wanted to cover in the presentation. So yeah, if maybe ask Nick to come on as well. So I think I can't see any questions yet, but as I was saying, I think this is a great example of a cross-sectoral project, and I think great way to start this session. So a few questions to start off with, just in terms of the kind of flexibility that you can potentially unlock from the kind of water pumping and other assets. Have you done any analysis on how this compares to cost of flexibility from other assets? Is it more cost effective? Is that one of the key reasons of kind of potentially pursuing this?
Well, the first thing is there's a lot of it. It's relatively well distributed, and obviously with serving the population, what we tend to find is that there's a good correspondence between where the electricity networks go, where population growth or industry is driving electricity usage is quite similar with.
Sorry,
with
I'm on the show and tell. I'm not speaking, obviously, but
okay, not sure
okay.
who that was.
No, I can. Hold on.
Can somebody mute Jonathan, please?
Yeah, the assistance, Jonathan. I'll carry on.
Sorry, Gary, go on.
So yeah, first of all, there's quite a lot of it, and it coordinates well. The big issue we have there is not so much around the price of it. It's the fact that the price that's on offer hasn't motivated large volumes of the water industry sites. So what we're actually looking at it is more from the opposite end of what do we need to do to enable it. What we don't want to do is just put an open check book out, because that really would be significant market distortion. What we're looking at here is actually trying to find alternative mechanisms. So indeed, in OpEx terms, we would like to see the flexibility on offer for £0, and actually, again, I'm quite cautious to use the term quid pro quo, not just because it's difficult to say, but because essentially what we'll be looking at is a situation where the flexibility from water companies would be embedded first, ahead of them going out to procure anything else, but obviously finding other more appropriate benefits that would motivate them to be involved, but ones that are deemed acceptable as to the regulators, doesn't inhibit other providers.
Understood. So just to summarize, Gary, so there is a very high coincidence, technical coincidence, and there's a lot of confidence that they would kind of have the type of flex, and also they would have it during the times that the system might need it. But there are some potential structural issues, and therefore there is a broader UK PLC benefit of addressing and removing those barriers, so that such a large amount of flexibility is available, on top of which other sources could kind of build off of. That's the thinking. Is that right?
Your summary was far better than the original answer.
No, I can't.
And just to add on to that, I think the sort of like, when you're looking at it from a whole system UK PLC perspective, is that we are regulated utilities. We're not doing this with any kind of person. It's thinking of that water companies, electricity companies, are both delivering services to largely the same customers. Most places have an electrical and a water connection, so it's a benefit which we can sort of stack together with that same customer set.
Got it. Thanks, Nick. And just picking up another point that you mentioned, Gary, which is motivation, which I found really interesting, because it feels like for projects thinking of, we as SIF want to see more cross-sectoral projects, and that aligning motivation is actually a critical point. Like, can you align on what they want and what you want? Otherwise, it's quite difficult to make that work. From your work so far, how much is kind of carbon reduction versus cost or kind of revenue generation a motivation has been for water company? Why are they kind of doing this?
So that's a really good question, because that actually takes us right back to the very first conversations of why the Flowers project originated, and that was through speaking with the heads of energy at water companies, and their challenge is significant. The net zero targets are really difficult, because for many industries, the carbon is a result of their own production processes. But to put it in quite impolitely, every time any of us flush our toilet, we are exporting our CO2 to the water industry to deal with. So it doesn't just have to take its own production processes and get those to zero. It's actually got to do a vast amount more, whether that be through offsetting, whether that be through renewables and exporting electricity. The net zero challenge is it's maybe not significantly harder than every industry, but for the majority of industries, their objective is a lot harder. So it's absolutely carbon was the original trigger, but looking at it across the board, the benefits are multiple, and not only that, the type of flexibility we're looking at from them isn't about firing up a gas engine or a diesel engine. It really is about taking processes that need to happen anyway and just doing them in a far more optimal fashion.
Understood. Thanks, Gary. I guess a little bit of follow-on question from that. I guess there is going to be revenue benefit for the water companies from doing this. As you said, it's not going to be a zero cost flexible. They're going to potentially participate in the market and provide flexibility to you. Is there any thinking on potentially how that value gets distributed back to water consumers?
Yes. So ideally, what we would like to see is, because of the closer ties that would occur between the two control rooms, sharing of understanding around operational requirements, process scheduling, etc., that would enable us to have a far more active understanding of what they're doing and relationship, and certainly one of the expressions from the water industry would be being able to get an awful lot more renewables onto the system without having to put expensive A&M systems, etc., in place. I appreciate these are the challenges for the project, and so we're not at this stage making that proposal. What we want to do is make it fact-based, so understand that, and that's part of the next phase of the project. I'm sure it will come up with accusations of distortion or queue jumping within enabling connections, but just putting that aside for the moment, as difficult as that is, what we would want to see is the whole system efficiency. First of all, reducing costs. If they can get more renewables on, it will reduce their overall energy costs. It will also reduce the flexibility costs that would otherwise have to be procured with the market. So we would hope that that would transpire through to reduced operational costs in both water and electricity, which would be seen through through lowered water rates. It would be seen through lowered GEOS costs, as well as the UK PLC net zero contribution as well.
Got it. Thanks, Gary. I mean, it's really fascinating. I think this kind of cross-sectoral thinking and how we can kind of overall optimize the system for kind of, for consumer benefits. I have a lot of follow-on questions, but I'll hold off because there is a question from the audience. The question essentially is kind of linked to something that we've been talking about. I think you mentioned, which is the kind of technical compatibility. How does the locational and dispatchability or flexibility from the water sector compare with other forms of flexibility, like EVs or demand side response from homes, buildings, or electrolyzers? And I guess there's a question on likelihood of it being reliable and cost competitive. I think we've covered these points, but maybe just summarize. That's okay, guys.
Yep. So there's it's not just a single asset type we're looking at. There's a number of industrial processes, and that's the reason we've got 16 use cases. Some of them ranging from almost an arbitrary shifting of processes that were set up in the past to operate during a fixed window, or quite simply through two set points, an upper and lower pumping set point, and they just happen. Is actually bringing those in and managing them, and in some cases that would mean that they would just change their behaviour now and into perpetuity, but that shift would reflect more so the demands on the electrical network, which was never a consideration when the profiles were originally set up, through to some other stuff which is more dispatchable, is for shorter duration, and is generally in a higher capacity delivery. So there's not just one shape of flexibility for going forward. There is a range, and they do different things. But what I would like to see, certainly within if we get alpha funding and support, is actually to look at probably the first 6 or 8 of those, which are less so in the dispatchable, but more so in the embedding. And what potentially happens there is it pushes back the time at which you then need to go to the wider market to procure flexibility in, because what you're just trying to get is conducive behaviours out of some of your highest your highest demand customers on the network.
I think, and also just to add to that, I think this question sort of quite neatly articulates what the challenge of alpha and beta is we need to have a fact-based proof of what the reliability and competitivity of that flexibility is. We have some assumptions about the sort of dispatch and locations. We need to prove those through the work in the alpha and beta. So that is very much what you're attempting to articulate through the rest of the project.
Got it. Thank you so much. I think we're just on time. Thank you so much, Nick. Thanks, Gary, for the presentation and taking all the questions. Again, yeah, very fascinating and a great example of a cross-sectoral approach to system flexibility. Appreciate your time. Thank you so much.
Thank you
very much. Thanks.
So if we can move on, could I please invite Chris, Laura, and Mazer maybe for the diversified flexible queue management project, which I think neatly picks up from where the previous project left off. Over to you, Chris.
Okay, yeah, good morning. Yeah, check the microphone. Good morning, everybody. Chris Goodhand, Northern Powergrid. I'm looking after the SIF program. So this is diversified flexible queue management. It's a project between ourselves, WSP, and NG ESO. The next slide, please. Okay, next slide again, please. And the next slide again, please. Okay. So a little introduction to the problem. We all know that we need to meet net zero, and the clock is ticking, not very long to go. In order to do that, we need to produce much more renewable electricity. we're ever going to meet the increased demand that transport and heat will place upon us. And now to do this, we need to be able to connect more generation and more demand to the network. And to do that, that requires available network capacity. Once that capacity is all used up, we have to build more capacity, and that takes some considerable time to do. You're into relatively major civil engineering to do that. So if we've got a system where there's not a lot of available capacity, is there a way perhaps of looking at the types of generation demand that we have attached to our system in order to try and squeeze a bit more capacity out and make better use of what we've already got in the existing network, whilst we get on with building the additional capacity. Can I have the next slide, please? Okay, so if we look at what we traditionally do when we're actually looking at capacity and looking at generation connected at a particular point, we will have a look at the generation that's to be connected. We will make an assumption that everything connected will provide its maximum output at any particular moment. And once we've added all that up to the available capacity, we'll regard that location as full and no further capacity actually available. However, if we can have the next slide, the real world is not actually like that, is it? We know that the sun doesn't always shine, the wind doesn't always blow, and if you've got a battery, you can back it off. You don't necessarily have to actually be using its output at any particular time. So if we start to consider this diversity between the generation types, is there some more capacity that we can actually squeeze out of the system, is the question we've been looking to answer. You know, we think that's probably the case. We've considered diversity forever in our design of the LV system, so it's not a concept that we are unfamiliar with, but we are into a slightly new game. So if I can have the next slide. So if we consider all this diversity and then say, well, okay, how is the real world behavior of the generation likely to be? And we start to look at that, we expect that there might be some available capacity that we can use to connect additional generation while we actually get on with building more network to actually support the longer term view. And this project is all about exploring how we might do that, what issues we have, how we can dynamically manage the connection queue at any particular point, how we can regard the generation that's actually there and its inherent characteristics in order to exploit that diversity in order to see if we have more available capacity. So that's the problem. Mazza and Laura have been working very hard to actually answer some of those questions. So I will pass it over to them to tell you how they've got on with that.
Thanks very much, Chris. If we can go to the next slide, please. Another one. So just a brief introduction. I'm Mazhar Syed. I'm an associate power systems consultant at WSP, and I was leading the work package 1 of this particular project. So the objective of this project were delivered through 3 work packages. The first work package looked at defining the problem and quantifying the problem at hand. The second work package looked at the regulatory barriers and any opportunities that we might have. The outcomes of each of these work packages, 1 and 2, directly fit into development of use cases and high-level benefit analysis in work package 3. If we can go to the next slide, please. As part of work package 1, we developed and verified 2 hypotheses. So the first one was that the actual available capacity at a GSP is much higher than what we currently consider as available. So this is by means of considering dynamic headroom that is available at GSP. The second one was that this dynamic headroom, this actual available capacity at the GSP, can be effectively utilized if we consider the diversity of the generation mix. So if you have a suitable composition of generation mix, then this dynamic headroom can be effectively utilized. In order to do this, we screened 40 GSPs within the NPG license area, and we quantified the dynamic headroom at each of these GSPs. We relied upon publicly available data to undertake our analysis from 2019 and 2022. Just a snapshot of this analysis is presented in the right-hand bottom corner graph. If you can go to the next slide, please. As part of Work Package 2, we reviewed all the various policies, network initiatives, and regulations that are available out there for connections management, connections queue management across the distribution and transmission. Some of them are presented on the screen just now, which included NGSO 5-point plan, the Tech Amnesty, Access SCR, and SQSS. If you go to the next slide, please. At the same time, it was very important for us to engage with stakeholders to understand their point of view and their thoughts on the current existing connections queue management, and also to understand what would be the change or what would be their thoughts if we bring in this diversified flexible queue management. So we set out to identify a few stakeholders and assess their inputs based on the likely interest and influence over the outcomes of this work. We developed a questionnaire which was passed on to our stakeholders, and then we also arranged 30-minute interviews with each of these stakeholders to gather their feedback. We've had good sessions over the past couple of weeks, which is now directly feeding into our work in Work Package 3. If we go to the next slide, please. So the outcomes of Work Package 1 and Work Package 2 have now allowed us to prioritize 8 GSPs for further evaluation. Now we are working towards developing use cases and demonstrating the high-level benefits that can be acquired when we incorporate the diversified flexible queue management. Moving forward, we will be taking wider network constraints into consideration as well. This work is still ongoing and is expected to finish next week. The next slide, please. So coming over here, right at the beginning of the project, we had set forth some hypotheses that we knew. We had a feeling that by utilizing the flexible, the diversity of generation and load within the network, we could enhance the hosting capacity. So through the work that we've done so far, we've been able to verify this hypothesis, and now are optimistic and excited to be proceeding to the next stage, that is the alpha stage, to develop the proof of concept. Now we are working towards refining our objectives and work plan for the alpha phase. That'll be end of my section, and I'll now hand over to Laura.
Thanks, Mazza. If we move to the next slide. So good morning, my name is Laura Brown and I'm the Commercial Manager for Flexibility Services in Northern Powergrid's System Flexibility team. So thank you for your interest in this project, and I'd just like to briefly summarise our further discovery phase dissemination plans. Next slide, please. So we have 3 routes in addition to the show and tell today. We're going to deliver a more comprehensive show and tell session and make that available online. There'll be outcomes posted through our media channels, and we'll be preparing a paper for the IET Future Power Systems Conference later in the year. Next slide, please. And I'll quickly go through the conclusions to leave some time for questions. So the next slide, what we've found in this study is that just what we thought, that the discovery phase has shown some really promising connection timescale benefits from taking diversification into consideration for both generation and demand. So the next steps that we're going to evaluate through in the Alpha project is verification of these assumptions and models using real world network and customer asset data. And we're going to establish the cost benefits to both the network and to our customers' connections, what the benefit of that, getting them on quicker, is going to be to their business models as well. And we're going to refine the methodology for incorporating diversification of resources for unlocking more dynamic headroom. That's me. So the next slide is just a thank you from us for your attention and an open opportunity for you to ask questions. Thanks.
Super. Thank you so much, Laura, Mazer and Chris. Yeah, great presentation and really exciting project. I think looking at kind of unlocking diversity of supply and flexibility for accelerating connections. So I think there's a couple of questions. I'll maybe start with that, and then I have a few questions as well. I think there's a clarification question maybe to you, Maziar, which is, can you please explain how the diversity factors are calculated, and maybe just outline some of the key assumptions made when you're calculating that, please?
At this stage, we have had to make some assumptions in terms of calculation or the consideration of diversity factors that we've used, and it varies. So, for example, for the demand itself, we've used what is typically used, what is found in literature for distribution networks, which was around 0.65 to 0.7. So this was the assumption that we've used for the demand. Now, in terms of the generation that we've used, what we've done is we've used location-specific data for solar and wind. So what is the solar radiation at that point? What is the wind profile at that point? And we've incorporated this into our analysis as well. So this has informed us of the results that we presented today. But moving forward, as we said, so we still need to verify the assumptions that we've undertaken. We still need to verify the models that we've used. And this is what we plan to do in the next phase of the project, the alpha phase.
Thank you, Maziar.
Also worth saying that an awful lot of academic and industry work has gone on to work out what these diversity factors ought to be. So there are a sort of set of industry rule of thumb numbers that we're actually using. I think as we look at the next phase, the alpha or beta phase, while I think we will probably spend some time looking at what those diversity factors are, I can't see us doing anything like the large amount of work that's already been done in this particular area.
Great, thanks, Chris. The diversity factors have attracted a lot of attention in terms of questions, I think. So, do the diversity factors depend on asset health? Is it a function of asset health, Maziar, when you're looking at? Do you know if the literature has kind of looked at asset health as well in correlation?
Yes, definitely. I mean, and this is a very good question. But for our preliminary analysis, we haven't considered the asset health. But moving forward, again, this is another factor that should be taken into consideration to try to understand what would be the impact of asset health on unlocking this sort of dynamic flexibility that we will have at the GSP.
Thank you. Moving on, I guess another question on diversity factors. Do these factors depending on historical data? So, for example, do you look at generation profiles over time, or is it more a point-in-time analysis?
Well, it's a great indicator. So that's what we've done. So we've used the historical data that was available to understand what the diversity factor was. But again, it does vary from year to year. But utilizing this data, we would be able to perhaps predict better diversity factors moving forward. So yes, it is a good indicator.
Like Manu, it's always obviously that it's very dependent upon the availability of the renewable resource, for example. So some areas may have different diversity factors based on their available resources. So I think there will be a key element of this study is utilizing the data sets that we have for regional and national pictures when it comes to available resources.
Got it. So I guess that's one of the complexity in your project that you perhaps need to validate going forward, is that it's a function of many different things. I think it's got a spatial element, it's got a time element, it's got a asset health element, which I guess at the moment you've kind of relied on kind of good literature to look at. But yeah, as you said, the focus of alpha is perhaps kind of ground truthing some of that going. Yeah, so I think that's really interesting. Got a few more minutes.
It's a complicated, just on that, Manu, it's a complicated issue. You're quite right. You can start to take, temporal issues, locational issues, all these things into account. But if we're not careful, we embark on a research project, which has some very interesting academic outcomes. But what it actually doesn't do is solve the actual day-to-day problems that we've actually got. So, we will build on what has gone before. We will probably incorporate reasonable safety factors into that. We will then verify that is a reasonable approach, because what we're involved here in trying to do is to get more people connected faster. So it's very easy to go down a rabbit hole with these things. So we just need to keep reminding ourselves that we are, in this particular case, we are engineers and we are not the scientists in this one. So yeah, very easy to get distracted if we're not careful, and we are very keen not to do that.
No, I think it's a great reminder, Chris, to not lose focus on going into some of these academic rabbit holes. So I'm with you on that. So as I say, a few more minutes. Maybe the one question I had kind of linked to this was, have you kind of found from your analysis in terms of what you need to understand from the asset to take some of these calls, is there any of this information missing from the field at the moment where we perhaps need additional monitoring to kind of cover some of the gaps? Yeah, have you kind of done that gap analysis?
Yes. I mean, for example, as I said, we were relying on publicly available data, and the data that we had was at GSP point, so metering point at a GSP. But this was sort of an aggregate data set, which was a sum of the loads and generations within that particular area. Now, in order to understand and do our analysis, we've had to make some assumptions and then sort of start to separate out this total power flow into different profiles. If we had data or more granular data of the generation and load within the distribution network, then our analysis would be more accurate. But still, I think that's why moving forward is to trying to get real world data, getting data from asset owners, and then incorporating that into our methodology to make it more accurate.
Brilliant. And I think that's a good point actually for people participating in it. Perhaps if you're kind of renewable development operators or companies, etc., I think perhaps a good opportunity to kind of share data for this. I have a couple more questions, maybe looking forward a little bit. It might be hard to kind of answer this point, but it might be interesting to just pick up, which is how might the cost of this kind of unlocked network capacity compare to traditional reinforcements? I know there's a whole complexity around the methodology around kind of doing that, but maybe keeping that aside for a second, do you have a kind of sense of scale?
Yeah, I think there's two elements here. There's we're doing this to help with connection speed, if you like, so to help put connections on the system ahead of reinforcement works. So it's more a speed thing rather than a cost. So the cost benefit of that is that the customer's connected sooner and is started their business model ahead of the original prediction. So that's the real benefit. From a cost of traditional reinforcement, it's not apples with apples, I think, if that's fair to say, because this is really just looking at the queue management and making the decision of what of the available capacity we have, how is the mix of generation and demand types we've got on there, and then some real-time data of what the network's actually doing at particular points. Can we make some more intelligent decisions about? I know the word Chris used was squeeze, but I don't want to scare anyone. That would still be a very safety-driven decision about putting on new capacity, but it's just about managing that capacity once it's on board to make sure that safety and resilience isn't impacted.
Got it. So I think we're just going to run out of time. Maybe just on that, a follow-on question, Laura. That's going to be my next question. Can you give the audience a sense of how much faster this process can be? Because you have a good sense of how much reinforcement takes. Can you just tell us how quicker this can be?
Well, at the moment, because we've been focusing on the GSPs, because that's our longest timescales for connection at the moment, where we've got connections that require some transmission upgrade work as well. And due to the works in our area, sometimes that can be 10 years or more for a connection time slot based on the volume of connection applications we've got at the moment. So we're hoping that it brings people ahead of that 10-year wait. So that's the sort of timescales. There'll still be a number of years, perhaps, just to work through the queue. So I'm definitely not going to give you a date or an increase, but we're hoping to really move down from this waiting for a decade to a more traditional sort of connection queue timescale, if that makes sense.
Thank you so much, Laura. That's fine. I wasn't looking for a precise answer, but I think that's really exciting that you can kind of accelerate that queue process, which I know is on everyone's mind from a net zero perspective. So I think with that, we're at end of time. So thank you so much, Laura. Thanks, Mazhar. Thanks, Chris. Great presentation. Again, a super exciting project. Yeah, really keen to kind of see where this goes. Thank you so much.
Thank you.
Thank you, Manu.
Thank you.
Thank you. If we move on to our next presentation, which is Power Block. Yeah, if I can please invite Jim and Scott. Jim, am I handing over to you
Good
first?
morning.
Morning.
Morning all. Hi, Scott. Yeah, Manu, I'll do most of the talking, I think. And is it Chloe in charge of the slides?
Yes.
Lovely. Good morning, everybody. My name's Jim Scott. I work for a company called Grid Edge. I'll introduce us shortly, but this is a project that we've been doing with Scott, who's here. Scott works for UKPN. The project's been led by UKPN, but we've also been assisted by Northern Power Grid, including, very helpfully, Laura. Thank you, on the last project. If you could move us forwards for me, please. This is what we're going to talk to you about today. We're just going to go over, what the problem was and what we think the solution characteristics feel like following the discovery phase. And we've got quite a clear view of that now. And then I'll wrap up on a bit of the outcomes that we've had over the last few weeks of work and what we think will happen next. So first up on the next slide, please, is our description of the problem. So the problem posed was the DNOs are seeing little flexibility coming into their markets and systems from commercial buildings at the moment. We're a data science, I didn't introduce ourselves. So Grid Edge is a data science company that works in the built environment. We work for commercial property owners. If you imagine things like shopping centres and airports, they'd be a typical customer for us. And sure enough, none of our customers are actively participating in flexibility markets. But there is a gap there. There is an opportunity. Commercial buildings have got inherent flexibility inside them. They have the ability to adjust their power curve within constraints. And the reason it's really attractive to DNOs is because it's near ubiquitous. It exists in most commercial buildings. Commercial buildings exist more or less in most postcodes in some description, certainly in urban environments. And it also doesn't require any capital outlay. So it should be relatively cheap. If only we could unlock it. The problem becomes unlocking it. And when we look at this type of flexibility that we have available in commercial buildings, that is the bit that makes it look more complicated compared to a battery or an EV or something a little bit more conventional. So the problem is, how can we extract this flexibility to support the networks? The next slide summarizes, I suppose, where we, some of the headline things that we think about this type of flexibility. So it's characterizing that consent. So for building operators, what it means for them to release this turn up or turn down response from assets that run their buildings, they need to understand the impact on their buildings. That sounds straightforward, but is often missed in existing propositions. They manage energy in the context of carbon, comfort, and cost. All three, not 1, 2, then 3, all three together. And they operate on about a day ahead basis. Maybe on a Friday night, they'll think about Monday morning, but that's about it. They don't look 6 months ahead. So to make flexibility services work for operators, and this came out loud and clear through the discovery phase, it needs to be on their terms. The engagement needs to be on their terms. The next slide, therefore, kind of a couple of slides here that characterize the technical and propositional characteristics of what they would engage with. And this is our findings, not just over the course of the discovery phase, but in testing some straw man propositions with different customers, actually trying to sell some of these propositions as well, which is quite interesting. And things have gone well and badly, erratically, depending on the way that we've pitched our service to two different existing customers that we have. I'll talk a bit more about that in a moment. So what does on their terms mean? Well, it means aligned to their timescales, measurable, they're very data driven. And what they mean is, if there's a complaint, I want to show the person complaining that it was okay, it was actually comfortable, I was doing my job as a building operator. It has to be transparent in its impact and the way that it works. They don't want to be fleeced. They don't want to be taken for a ride. They don't mind you making money out of them, but they want to know what's going on. And it needs to empower our building operators and not override them. So these are the technical things that we have to achieve in the solution. From a propositional point of view, on the next slide, please, Chloe. Building operators view their buildings, and this really came out in the work that we did, as I'll talk about in a moment. They view their buildings as personal. They're personal to them. They are full of people whose names they know, and they completely reject this idea of being aggregated into a blob. It is just megawatt hours available for dispatch. That is the opposite of what building operators serve their tenants with. They serve you with receptionists, floor guides, maps. This building, the way that they think about their buildings and their life as a building is very personal and very unique. They are not the same as the next building, even if they look the same to you, even if it looks like a glass box. To the people that operate them, they have their own personalities. Any income in this space is always treated as cherry on top. It's not treated, interestingly, in the same kind of bracket as energy efficiency savings, which I thought was quite interesting. It must not bring out all of the procurement professionals at the facilities management company. That was a big blocker. Procuring anything in a built environment setting is a nightmare. That's why buildings don't get upgraded very quickly. So anything that we do here must be simple to procure and engage with. And the other thing that came out loud and clear was there is little alignment between what the building operators see as their problems, run the building properly, and what the DNOs describe as their problems. Listen to the last two presentations, really interesting. Why? Nothing to do with whether people are hot or cold or not. That's the world. Take the bins out, make sure nobody's complaining. They treat the network obviously as a service. So the other big thing that we found was that for this type of flexibility, actually the mechanism is there in the dynamic market work that UKPN have been doing. The flex is there. The customers are ready to participate, but the market we describe here as undeveloped. So actually, it's there for the taking. It's there to be done. It's not simple, but there is, following this work, a clear path. There is a timing problem and there is a consent problem, I suppose, but it's not blocked. On the next slide, I suppose I'll go and talk a little bit more about some of the desktop stuff that we did. So these are the folk that we went off and spoke to. We did semi-structured interviews across a range of organizations, all in common. They all own their own buildings and operate their own buildings. So think about like tenanted offices. They're always really tricky and are a bit of a nightmare in regards to decarbonisation in general. And the other thing that they have in common was they always had net zero goals. There are still organizations that can't really talk about decarbonisation in a mature way, often finance houses. They just treat buildings as assets. We just couldn't find anybody to interview in those buildings because they don't employ sustainability professionals. We also went and engaged with the DSO teams, and thanks very much to UKPN and Northern Power Grid colleagues for assisting us with that. The project itself, so if you could move on to the next slide for me. This is what they said. I won't dwell on this one too much, but building operators have their comfort, carbon and cost, and they are equal, and they are completely different to what the DSO said, which is not a surprise, right? You're in completely different sectors. The thing that the building operator can align behind is decarbonisation. And that isn't just within their four walls, it can be a bit further out as well, which I thought was quite interesting. And the complexity of engagement, the costs ROI often came up to that last point on the right. So we think the answer to this, if you could pop to the next slide for me, is if we can build something that meets these two user stories, we will win. We will unlock that flexibility. DNOs will be able to turn things up and down on terms that are acceptable to commercial building operators. They're a little bit high level. There's obviously quite a lot of depth that needs to be done underneath here, but this is what the market is telling us that we should build for. At the moment, we have an offering as Grid Edge that looks a little bit like the next slide, please, which starts with a high-level energy tracker view. So it's just fiscal meter data. It goes into a deep dive into a building management system. And at the end, we do quite a bit of work around flexibility for, I suppose, capacity and balancing market price signals. So that that at the moment is where we see quite a lot of our traction coming on that far right hand side, where we're switching things on and off inside a building due to electricity pricing. And obviously we want to change that to start switching on and off due to DNO signals as well. And that's where the dynamic market fits really well. The next slide, if we pick that one on the left hand side, that energy tracker bit, this is a sample of some of the sites that we have, no geographic bias to any of these, where we've normalized the shape together. So we've got about 1,000 MPANs or so in here. And one of the things that we wondered about was whether we could spot which buildings have flexibility just from their shape. So these are different shapes that we have in the sample, and you can see the orange one looks a lot like a data center with solar. The kind of light green one along the bottom, that's a pub. And the red one in the middle, that's our most flexible site that we have in our portfolio. It has 400 odd kilowatts of heat pumps. It has electric vehicles in it. It's got solar on the roof. It doesn't have any batteries because building operators don't want batteries. They want cost and carbon reduction. And you can see it's not obvious why that would be the flexible one. So we found very little correlation between flexible assets deployed and shape. But once you've got that building management level data, that what's going on in the building, what kits have you got data, you already know the answer. So kind of working bottom up in the commercial industry seems to be the best approach. On to, I suppose, next steps to wrap up. So on the next slide, we've got a bit about how our sort of thinking has evolved. To just summarize, so timing and engagement remains a challenge. There's a lot of the DNO's voices. We know the pathway, we're working on it. Well, that's very difficult for us to then go to market and talk to our customers about properly, because it needs to exist. The static market's been a really helpful bellwether and has got us going in the right direction. So we're very much looking forward to, when those dynamic markets start to mature, is our best word for it. We've learned that engagement, I've picked off the bottom 2 bullet points here for time. Engagement is absolutely best packaged with familiar faces. Building operators are not keen, or building owners are not keen on having yet more parties drop in. So facilities management companies are the way to go. I suppose the final piece is the next slide, which is around data sharing and integrations. The geospatial problem that's been talked about quite a lot already, that certainly applies here. This market request and response integration exists, and the maturity of demand forecasting for dynamic markets is something that DNO's highlighted as a gap for them. And the next one is the final plan, which is what we will do. The main one is we will wait for the DNO dynamic market to be ready, because that looks like a good fit for this type of flex. And that's really what I want you to hear is if you build it, the flex will come, but it will need assistance. Building operators will need a little bit of help, because you're not talking to them just right at the moment. You're saying recruit and aggregate and dispatch, and they don't want to be spoken to like that, is the blunt way of saying it. Due to the delay, we're probably thinking about going in for a possible NIA funded project in the future, but I suppose one of the nice things about the work that we've done is this really does put it back into Grid Edge's court here. It enables us to have quite a strategic conversation about next. Thank you very much. That's the next slide says any questions, please. So welcome any questions. I just want to say thank you very much to Scott and his team for his support, and thank you very much for listening.
Thank you so much. Thanks, Jim. So I think it's really good, following with this project from the previous one, which kind of looked at the kind of top down and then looking at, one potential source of flexibility and kind of unpacking some of the complexities that are in there to kind of do this and the potential there. I think it's a great kind of follow-on presentation. So I haven't seen any questions from the audience so far, but I've got a few. And I think having worked in commercial building management controls, I think this project, I kind of sympathize and empathize with a lot of the points that you raised, Jim. The first one was, I remember, I think there was previously an innovation project done, I can't remember the name of it, which kind of looked at, I think, hotels in the UK as perhaps one subset of commercial buildings, where I guess one of the complexities was when the kind of system needed it, that's when the load became unflexible or inflexible in commercial buildings. So for example, you can think of like a day like today where it's really hot and the system is under stress. But hotels, that's the point, they wanted to kind of blast their ACs for everyone to keep their comfort level high. Have you looked at some of those things in terms of how good a fit are some of these commercial buildings, or do you need to do more segmentation to assess fit with kind of system needs?
I think that comes down to the personalization point. So yeah, one of the not quite hotels, but cinemas is a sector that we've worked with quite a bit. So they're quite similar, right? Actually, cinemas are specified for an era where the seats were all a lot closer together and you had a lot more people in there. So what we actually discover when we go out is that all the AC plant is wildly over specified and oversized. Now, does that directly equate to there being some flexibility available? Maybe, maybe not. On those real peak extreme weather times, it's hard to say, but I think that's okay. I think that the advantage of geographic ubiquity and very low cost, so it's always going to be cheaper than a battery or cheaper than some other no wires measure or whatever, right? I think that means that it's still a sector well worth looking at. I think what that report is picking up is your building manager immediately going, we can't possibly engage with this because sometimes it has to run at 100%, therefore no. And that's quite lazy, right? That's not helping. When you can talk about that as a carbon impact, you can diffuse that opposition very quickly. And that's been a really strong bit of learning over the last really 5 years for us. Is that's where the alignment is. The moment you start talking about markets and costs, you meet the procurement team and a lot of barriers and liabilities appear. Talk about carbon, a lot more gentle, and everybody can agree, no arguments. Yeah, a dichotomy.
Yeah, no, makes sense. I mean, just to follow on question, and sorry to kind of dive this into a little bit more. Again, one of the challenges I remember was the kind of part load efficiency argument you always used to get from like HVAC operators, even if it's oversized. Just from a part load efficiency perspective, they used to run it on full tilt when it might not be required. How have you overcome some of those conversations around oversized equipment and potentially running it part load because there's a kind of wider benefit that they're not really thought of yet?
Yeah, so I think I didn't dwell on this probably enough, but in one of the user stories, we used the word trust, and that's the word. If you trust whoever it is that's running this for you, no arguing. It's okay. It's all figured out. The moment that you're having a conversation about basically that conversation, you're explaining, and I think you've lost the conversation. And you have this with price volatility as well. The way that we build trust is by helping with energy efficiency. So our facilities teams that we work with have an energy efficiency problem. They keep getting barked at by their customers about net zero when they don't have, they've got a lot of work to do. And over again, you see case studies about 10-15% energy efficiency savings being available in commercial buildings. Well, buildings are 40 years old. What's been going on for the last 15 years? Like, it's not like it's a new thing, right? So there's always, once you've got a building nice and tightly controlled, we always find you've got a good engaged team, and then you're at 100% energy efficiency in the team's head. Now they'll look for cherry on top stuff, and it's not about the technical deep diveness of it. It's about the alignment of attitude. And once you've got that, then you get the imaginative bit of that building manager's challenge, not the blocker bit.
Yeah, and I think it's a great example of, as you say, at the outset of it, it might look technically complex, but some of the social elements like confidence building and trust is such a critical aspect in bringing forward some of these assets, which I think sometimes gets kind of lost in some of the technical discussions. So I think,
and you can hear it in the language that everybody in this sector uses. There's a gatekeeper to this type of flexibility. hang out in the basement and they fix your air conditioning unit, and they are best never seen. They're doing a good job when they don't see a building user, but they're the people that we need to empower if we need to release this. And that, you know, the most successful organizations in their net zero journey that we've met have been the ones that value those engineers highly. Yeah,
Thanks,
I think
Jim.
it'll apply to this too.
Nick has his hand up. I don't know if there's a question or.
Yeah, I did. So I hear what you're saying about the need for sort of personalization and a resistance to words like aggregate. How does that square with adding together sufficient volumes of flexibility needed to create a value to the DSO in terms of that level of flexibility? Because I might be wrong, but I don't necessarily picture in a single building offering the whole of offering significant value in terms of flexibility on its own, unless it's added together with other buildings acting in concert.
One of the comments that we got from the DNO side was that they keep dropping the threshold of participation, and that's gone down to, it's 10 kilowatts, was it, Scott?
In UKPN network, yep.
In UKPN network, and that was in an effort to get more participation. I think the plan would be to put that up in the future, because a bit like National Grid frequency response, they want to deal with a small number of parties, right? But that's not. But yeah, you're not talking market there, right? You're not using customer voice at all. You're using DNO voice. So I think the point is there's a translation layer in between the two. Something that does change that kind of fundamental point is heat pumps. Heat pumps specified for the coldest day, full gas replacement, great big tank of hot or medium hot water, huge, great big battery. Yeah, okay, you might have 1 or 2 cold snaps where it's at max, to Manu's point. A huge load. They could treble the load of a commercial building quite easily, or a college. And I think that means that the growth of that sector in particular, much more than electric vehicles or batteries, will put this type of commercial flexibility on the map for DNOs. It will make it of interest at scale. As for the aggregation piece, I do actually just think that that's a proposition and language thing. I think our view has always been that Grid Edge would work on the customer side, and we would want to engage with an aggregator. The aggregator's view has always been, we will reach into the building and switch stuff on and off, and they fail to do that manifestly in this sector. So I just think it's a proposition design problem. Hi, Andrew.
Hello. I'm not in this industry, in this side of things, really. So this is purely just really a very simplistic question. Have you had any discussions with the new hospital program and that side of things, with all of these many new hospitals proposed to be built and retrofitted?
No, we've not. No, we've not. I suppose I can bring a bit of Grid Edge's experience here. We find it's so much easier to work with buildings that are 5 to 10 years or older, because at new build, and I wonder what this would feel like in a hospital build, I don't know if they're PFIs or what, you have a lot of nervous cost engineering going on just before handover, and then a lot of settling in guarantee period just after handover. And that web of contractors and guarantees makes it very difficult for the operator to really influence the building at that window. Once they get to 5 years and all the guarantees fall away, suddenly we pick up those customers very quickly, because they go, oh, I couldn't mess with my CHP unit or my heat pump before, but now it's all out of warranty. I'm going to go and switch things on and off all the time. I'm going to get stuck in. And I think that's always put us more towards the retrofit industry. Or at least the existing building industry, rather than new build and capital projects. And the other thing, frankly, is timelines. We're a venture-backed startup. I mean, how long has it taken to get that program off the ground, right? We haven't got 5 years to wait around until an asset is built.
My limited understanding of the new hospital program is that it's not necessarily all new builds. So there's quite a number of retrofit projects, and I believe that the way that they are running those projects is different to that of past projects within the trusts. that could be an interesting avenue for you.
That could be really interesting for us, yeah. And I think I can see the facilities management industry getting more involved with that type of thing as well. If you think about the big engineering companies, they are taking on more projects, and they're not quite at heat as a service, for example, but I think they're nearly there, right? They are thinking about it. So I'd certainly be really interested in that, yeah.
Well, thanks. Just a bit of time, I think. Yeah, thanks, Andrew. I think I love that it's going to become more discussion. I think that's really good. But thank you so much, Scott and Jim, for that presentation. I think, as I said, it's kind of great to see one part of that flexibility portfolio deep dive and kind of hear some of the stories behind some of the challenges and potentially kind of unlocking it. Yeah, so thank you so much for your presentation.
Thank you, Manu. Thank you for your questions.
Thank you. So if we move on, please, I think we are now going to move towards a quick break. Yeah, so I don't think we're going to take quite 15 minutes. So I think if we aim to be back 5 to 11 to begin. So just as a recap, and maybe whilst I'm doing that, if I can ask the next presenters to get ready. I think it's Matt, Luke, and Andrew on the hybrid storage project. Are they? Brilliant. So I think just as a quick kind of background, I think we've run through 3 projects today morning. We've started looking at, how do you unlock flexibility from the water sector through the shifting currents project. And then we moved on to the diversified flexible queue management, which is, how can we use the diversity and flexibility in loads and the supply side to perhaps accelerate connections to the system. And then we did a deep dive into one of the flexibility solutions, which is kind of commercial buildings, and kind of understood what some of the kind of social aspects to those were in terms of complexities, and then kind of looking to unlock it both from, I guess, social and a market perspective. And then I guess through this kind of energy system journey, we move on to the gas system now, and kind of looking at kind of hybrid storage systems. So I think, yeah, I'll hand over to Matt, Luke, and Andrew to take us through the presentation. Matt, over to you.
Thanks, Manu. Yeah, hopefully you can all hear me okay. So morning, everyone. My name is Matt Hammond. Work in the innovation team at National Gas Transmission. I'll talk to you today about our project hybrid storage systems for site safety and efficiency. So next slide, please. So if any of you happen to be in my presentation yesterday, some of the background introduction slides are similar, so just bear with me on that. But National Gas essentially own and operate the National Transmission System, which is the UK's high pressure natural gas network. The NTS is made up of over 7,500 kilometres of high pressure pipelines, bringing natural gas onshore at the terminals and transporting it across the country. We supply natural gas to power industry and to the gas distribution networks, who in turn supply gas to homes and businesses. So we utilise compression on the NTS to essentially boost pressures and flow rates on the network to meet demand and build line pack, which is our way of sort of storing gas in the pipelines. We utilise over 70 compressor units across 24 sites strategically placed around the country. Next slide, please. So most of our compressors are driven by gas turbines. We take natural gas from the network itself and burn this as a fuel gas in the turbines. That means they produce carbon dioxide. Because we've got over 70 of these units, most of them are gas turbine driven. That means this is the biggest source of emissions on our network. Therefore, we're looking at ways that we can decarbonise them. So previously, we've run a number of feasibility studies which have shown that it's possible for us to fuel our existing gas turbines with hydrogen blends and 100% hydrogen. And we realised the largest emissions reduction comes from using 100% hydrogen generated from electrolysis using green electricity. However, due to the intermittency of green electricity availability, we expect that we'll need hydrogen storage on site in order to meet the demands of the turbines when renewable generation is low. Next slide, please. So in terms of storing hydrogen on site, there are safety regulations in place which specify that permits are required for storing more than 2 tonnes of compressed hydrogen gas. Currently, our compressor stations do not fall under these limits. These are the COMA regulations. 2 of our terminals do fall under the COMA limits. These have a significant amount of additional sort of safety and security measures in place because of these regulations. Solid state hydrogen storage is an emergent technology which can store hydrogen at high energy densities, but at ambient temperatures and lower pressures compared to compressed gas storage solutions. However, in terms of the flow rates and pressures from the solid state storage system, these may be too low for what our turbines require in terms of fuel gas conditions. And that is where compressed gas storage can come into play. So this project is essentially looking at the feasibility of a hybrid system where we have a solid state storage system and a compressed gas storage part, and looking at how we can optimize this using an AI tool. This means we can store hydrogen on our sites without entering into the COMA regulations. Next slide, please. To carry out the project, we've got a number of partners on board. So obviously ourselves as the owner and operator of the assets that we're looking into. H2Go are a technology company with a portfolio including the solid state storage technology and their high AI tool, which we've deployed in this project. The Manufacturing Technology Centre, a research technology organisation working across industries to support UK manufacturing, and they are looking into the system manufacturability and assembly. UK Power Networks are electricity distribution, as you've heard this morning. Wales and West are a gas distribution network, both of which may be able to utilise this solution on their own sites. They have an interest in supporting the project from their side. Finally, Nottingham University have expertise in solid state storage for hydrogen and are peer reviewing and critiquing our approach to make sure we're taking the project in the right direction. Next slide, please. So some general points on the sort of system requirements and developing the use cases. We know that most of our turbines can be repurposed to run on hydrogen, which means the rollout of this solution can be network-wide essentially, which is good news. However, the utilisation of the gas turbines varies from site to site, which will have an impact on the design of the system. So a turbine with high running hours may require a large electrolyser with smaller storage. A turbine with low running hours may require small electrolyser but larger long-term storage. We know that production of green hydrogen may not align with demand, which is where our storage needs to play a part. And National Gas, as a gas transporter, do not currently have a license to own and operate hydrogen production and storage assets. So we would need to identify the business models to overcome this. Next slide, please. So in terms of site selection, there's a few things to consider. I mean, the first point is that all of our compressor stations are different. There's no two are the same. So different equipment, different available space on site, different locations. So the water and electricity supply will vary, and that will play a part in how our system needs to be designed. We also need to consider additional use cases to the gas turbine. So we've previously run a project which was looking at the feasibility of fueling other assets like heating and diesel generators with hydrogen, again, to realise more emissions reductions from our compressor station operations. There's also potential for local hydrogen users who could sort of tap into our supply as well, and that would further build the sort of business case for this kind of system. And consideration of other hydrogen projects is a nod to our electrolyser efficiency project, which I spoke about yesterday, and also UKPN's Connectrolyser project, which we have been supporting. And there's potential overlap with these projects in the alpha moving into beta phase as well. Next slide, please. And I am now handing over to Luke at H2Go, who will talk us through the solid state storage and high AI tool. So thank you, Luke.
Yep, thanks for that intro, Matthew. So yeah, my name is Luke Sperrin, so I'm the CTO of H2Go Power. H2Go Power is a hydrogen technology company, and through this project we showed how we can apply our most mature technology offerings. So we've got our solid state storage on the left hand side, and then our AI optimization platform called High AI on the right hand side. So our storage system, so I'll start off with the left hand side, sits in the middle between the hydrogen production and the hydrogen usage. In this case it's the electrolyzer and the hydrogen turbine. We take the hydrogen gas, store it for a period of time, and then release it when it's needed. So storage is needed in terms of system resiliency, but also to make sure you're taking advantage of the best time to produce hydrogen and to use hydrogen, which often doesn't overlap. Our solid state storage is a containerized plug and play system that consists of material that stores hydrogen gas at room temperature, and then we can just release it when it's needed to balance supply and demand. We essentially house this material in carefully designed modular reactors, allowing us to get the hydrogen gas in and out as quickly and most efficiently as possible. The benefit of this kind of storage is that it's low pressure, so whilst maintaining really high density and low cost. The hydrogen gas is chemically bonded until required, dramatically enhancing the safety of the system, but also preventing hydrogen leakage. So these containerized systems can actually add up like Lego blocks to achieve the storage and high flow rates. So you can kind of expand the site as the site changes with its requirements, which is a really useful point. Now switching over to the HiI side, so we've got the HiI platform, which allows for complex hydrogen systems to be optimized based on data from that specific site. And that's that combination of data and algorithms that allows the creation of a virtual system, meaning that we can simulate it before it's being built for smarter investment decisions. It also means during operation, we can produce the cheapest hydrogen possible and then use that in combination with storage. It allows us to reduce build and operation costs by between 20 and 40%, as well as CO2 abatement cost reduction of around 10 to 20%. And basically this means we can target investments to decarbonize in the most effective way possible by identifying the low-hanging fruit and the quick wins. The software allows us to produce plots like the one shown on the screen to show emission reductions that can be met at what cost. Through our simulations of this project, we've showed impacts can be achieved with investment and informed design to decarbonize the power sector. I'll finish there and move to the next slide, and I think I'm handing over to Andrew to talk about the work they're doing at the MTC.
Thank you, Luke. Yeah, my name's Andy Perkis. I'm an advanced research engineer at the MTC. So working on R&D projects and design and build of machines for proof of concept, aiding UK manufacturing. So during the discovery phase of this project, we analysed the past runtime data of the turbines located at the site that's earmarked for installation. We identified the period for which the turbine saw the greatest consumption of fuel and mapped out the inputs and outputs of equipment for the creation, storage and distribution of hydrogen to support this historic use case. On the graph that you can see here, the fuel consumption for this period, looking at the lighter green line, you can see this turbine fuel consumption. As the turbine ramps up, fuel consumption is supported by the electrolyzer and the solid state storage. The upper line is the hydrogen remaining in the storage, and the blue line shows the hydrogen output of the electrolyzer. As the turbine ramps down and stops, the electrolyzer replenishes the solid state storage for the next runtime spike. And the black line that you can see identifies additional storage required to support this process. The next slide, please. This is a pictorial representation of an example layout that we look to take further into alpha phase. Our activities at the beginning of this alpha phase will focus on further developing this energy model, incorporating the electrolyzer type proposed by other electrolyzer projects, and also the turbine exhaust heat recycling equipment, as well as all the ancillary and balance of plant equipment required for the system operation. Alongside these activities, we will further research additional hydrogen storage solutions, performing a down selection process using comparative requirements such as safety, energy efficiency, equipment lifespan, capital and operational expenditure. And once we have identified this optimized configuration, we will move on to the design activities, performing a full system design and site layout, running through our design review process, ensuring safety is at the forefront. We will then identify the permit tree required for installation and develop a test plan ready for moving into the beta phase. And as part of the design activities, we will identify opportunities for the packaging of equipment into modules to aid in the transportation and deployment on site. I'll now hand back over to Matthew. Thank you.
That's great. And I think we can move on to the final slide as well. Just to finish off, just covering some of the things we want to cover in Alpha. So nailing down the use cases and the demonstration requirements. So we obviously want to demonstrate this on site and demonstrate the benefits that we are hoping to see from the system. That will lead us into a sort of full system design and get a more accurate view of the costs of this in terms of rollout across the network. We need to overlap with our electrolyzer efficiency project, which incorporates waste heat recovery from our gas turbines to feed into an electrolyzer. And then this hydrogen storage system would fit nicely in that. The aim is that we would demonstrate these together in the beta phase. As Andy said as well, planning and permits is going to be a big thing, policy and regulation considerations as well. It's not just a case of one day you can suddenly say, I'm going to start putting hydrogen into this turbine and start burning it. For the demonstration, we also need a test plan which demonstrates those benefits of the system just to prove it works. Engagement with local hydrogen users, there's the potential that there are industry users of hydrogen who could tap into our supply and continue to build and understand the business case for the full network rollout as well. So that brings us to the end of the presentation. So we can now move into questions, I think.
Super. Thanks, Matt. Thanks, Andrew. Thanks, Luke. Great presentation. I think really good example of, again, like cross-vector flexibility as well. I think we've got a couple of questions from the audience. I've got one clarification question to maybe start out with, and then Nick, maybe I'll come to you afterwards, which is the energy modeling chart. I think that you were showing did not have the power input into the electrolyzer. Was that like an optimization function? Were you also looking to optimize in terms of the input? The reason I was asking was, I think one of your previous slides essentially had carbon reduction as a potential objective function. If you were to have carbon reduction as objective function and you're trying to run the electrolyzer in line with perhaps when the grid intensity changes, how does it affect the overall operation? And does the system configuration still remain if the electrolyzer is kind of tracking carbon?
I think that initial energy model that we built up, it was something that was an initial one, something that we looked to further develop at the start of the alpha phase, and really feed into it some data on green energy production on the grid. So green energy on the grid, and feed that into that scenario further. So that's something that we'll look to take into within the alpha phase. I hope that answers that question.
Yeah, no, I think that's fine. Just a scope question, I think. And just as a follow on, I guess, to Matt was talking about in the last slide, which was looking at synergies with the solid oxide electrolysis project as well. I guess there's one question which I had, which was, if you were planning to operate the electrolyzer a little flexibly, I guess you have some operational constraints between whether it's a PEM or a solid oxide. I don't know what research there is in terms of flexible operation of solid oxide and impact on purity of hydrogen or lifetime of the asset. So I don't know if that's part of your considerations, Matt.
Yeah, I think it should be. So we're working with the UKPN's Connectrolyzer project, which is looking a little bit in terms of the flexibility of, I think, PEM electrolyzers. But however, we need to do that sort of separately ourselves, I would say, on the solid oxide system in terms of its flexibility and understanding that a bit more. Just to go back to your first question as well, I think H2Go's modeling did incorporate grid intensity into their AI model when they were looking at sort of the carbon reduction emissions, I think.
Yeah, that's correct. Yeah, we use the marginal emissions from the grid as well as we sort of did that with a lot of our modeling systems. Yeah, that's
super. Thanks, Luke. And then I'll just get the audience question, and Nick, I'll come to you in a second. I think Kieran's got a question, which is, I had a similar question as well, which was, how would National Gas be able to utilize the project's outputs? I think the assumption is that you are not allowed to own storage assets in the same way, I guess, DNOs and DSOs can't own electricity, batteries, etc.
Yeah, so that's absolutely right. So we obviously, as the gas transporter, can't own or operate storage or hydrogen production assets. So we need to.
Oh, sorry, Gary.
Okay, under the circumstances, desperately sorry that you had to send that email earlier on. It's not.
If you can mute Gary, please.
We're a very small business, and normally I have my hand in.
Sorry, Matt.
So I can
That's all right.
keep an eye on it. We don't do any advertising.
Do we know who's speaking?
Do any marketing. We
I think it might be
pick up
Gary.
business
Gary, could you go on mute?
Referrals and
Yeah,
repeat
I don't know if you
business
can
from
hear
our
us.
customers. So this is a very unusual situation for me, but you can rest assured it's one that I will seek to resolve as quickly.
There we go.
Okay, cool. Yeah, so yeah, basically as a gas transporter, we're not licensed to own or operate hydrogen production or storage assets. So we would need to consider the sort of business models for that going forwards for when we want to demonstrate it on site. We've got a company called Hydrogenous working on the electrolyzer efficiency projects. They're looking to develop sort of hydrogen hubs in the UK. There's the potential that they would take that on, and it would be a commercial venture for them.
Thanks, Matt. Quickly to Rob's question, maybe Luke, just a clarification question. In terms of long duration storage, how long is long? What's the duration of the storage in question here?
Yeah, so the way we're storing it, because it's chemically bonded, it can store for seasonal storage, because you're storing at sort of a 1% of the pressure for, and then basically 99% stored in the chemical sort of storage form. So we're talking about sort of a 10,000x less sort of leak rate as conventional storage systems. Though when it comes to sort of long duration storage, there is an economics question to be answered. So it's all about how much you're utilizing the storage, and I think that's something that has to be looked at for the solid state systems versus other sort of storage methods. I think it's more of an economics question, to be honest, but they are very well suited for that sort of long duration seasonal storage.
And what's the extent in which you, like from your modeling, I guess, how long would you need to discharge, or how long you need to hold to satisfy the turbine or the compression operation on the site?
Yeah, so at the moment, so we've got our sort of shipping containers, which we sort of saw in the picture, storing around 200 kilograms of hydrogen and discharging around 4 hours. So you can kind of see sort of the flow rates. And the idea is to meet those flow rates, you add those little blocks up. So we are, for this project, we did look at sort of a considerable number of these to sort of added together. But the good thing is they take up so little space that you can, they're very well suited for areas where there's land restrictions.
Yeah, the density helps. Thank you so much, Luke. Yeah. And Nick, you've got 1 minute. Hopefully you can ask a quick question, we can get an answer.
Yeah, hopefully this can be answered quickly. So in how where you are now in the alpha and beta phases, how much consideration are you giving to obtaining the electrical connection for the electrolyzer? It's not it. There's certain considerations there. I just want to make sure that those are being considered.
Yeah, it is a big consideration. So obviously this project is probably more focused on the storage aspect. The other project which we're running in parallel, which is the solid state, I get my words muddled, there's too much solid stuff going on, but the solid oxide electrolyzer, that's taking more consideration to the electrical connection. So we have UKPN on board that project as a sort of consulting on that aspect of it, and they're giving us some helpful hints about these kinds of connections. Like I mentioned, the Connectrolyzer project was looking into sort of new connections, flexible connections for electrolyzers as well. So we're sort of keeping an eye on the outputs of that as well.
Super. Thank you so much. I think we're out of time, and thanks for the question, Nick. Thanks so much, Matt, Andrew, Luke, for a great presentation, and thank you so much for answering all the questions.
Yeah, thank you.
Thank you. If we can move now to the Insight project. So from the gas system, we now move back to the power system to talk about future system stability. Jonathan, am I handing over to you?
Yeah, that's right. Yeah, thanks, Manu. Okay, good morning, everybody. A few of us are going to be talking about the Insight project. I'll begin. I'm an innovation project manager at SSEN Transmission. If you go to the next slide, please. So the problem we are facing as an industry is a result of unprecedented uptake of new cleaner energy sources on the journey to net zero, which is causing new types of oscillation on the electricity networks, not just in the UK, but across the world. So why is there a problem? Well, there's a move from fossil-based power generation using heavy synchronous machinery, such as gas turbines, which are effectively constant in their power delivery due to the large inertia of the system. However, asynchronous renewable resources such as wind and solar are very intermittent just by their very nature and pose a new challenge to our networks. Within the UK, electricity network, we operate at a frequency of 50 hertz, and this must be maintained continuously 24/7 within a very narrow range, and that range is typically 0.2 of a hertz at the side of the 50 in order to maintain a safe operation. And traditionally, electricity generators are high inertia systems, as I mentioned, that can cope with high transient instabilities, but new technologies are required for new renewable energy sources, and they are low typically in inertia. And these technologies are based on power electronics and often referred to as inertia-based resources. So just before we move over to Jacob, I'll just mention the partners. So that we've got University of Strathclyde, who are looking at state of the art in understanding oscillation methodology and modeling, which is a very complex subject. The National HVDC Centre, who've gone out to the industry for a stakeholder engagement, both in the UK and further afield. National Grid, ESO, and ourselves, we're providing information on oscillation events and historical experience. So over to Jacob for the next slide.
Hello, yes, I'm Jacob Kelly. I'm a Transmission Operation and Planning Engineer at SSEN Transmission. So I'm just going to have a quick overview of the project, what its objectives are, the benefits, and what we've done in discovery phase. So the real sort of long-term objective of the project is to try and deliver a virtual real-time alert and control system that can monitor and then provide actions to mitigate different types of oscillation events experienced on the network. If we can do this, we can improve the network stability and reliability. We can reduce the likelihood of network disruptions, and it is potentially a low-cost solution that does not require the contracting of expensive stability resources, either bringing on existing power stations or constructing new synchronous plant to provide that stability to the system. It also allows us to sort of act and react in real time to events that we haven't been predicted in the planning phases. So that's where it helps improve the kind of resilience of the network as well. So throughout the discovery phase of this project, we've been looking kind of globally and within the UK to get a real understanding of the problem and the best practice of what other people have done, where the industry's at, kind of what the kind of tools are that are available just now and where they look like they're going in the future. And we've investigated the kind of models and tools that we can use to simulate these network events, the kind of patterns they are, and look at how we can use those to design a system that can do this. Because one of the key things in designing this is we need to be able to test it in a meaningful way. Next slide.
Hi, my name's Fabian Moore. I'm from the HVDC Centre, we sort of led a bit of work on stakeholder engagement and trying to find out what the rest of the industry is doing. So we sent out an industry survey to 55 different organisations from across the electricity industry. We got 32 responses, including 11 from different system operators and owners. So that's across the UK, but also including Europe and other countries across the world. And so just as a pie chart there, just showing who responded to the surveys. And the largest category is other, and I think those are generally industry-led research groups or academic universities as well, and consultants. But the largest sort of industry group that I guess we're familiar with is the network owner and operator. So that's our background. And next slide, please. So just to summarize what we learned in the survey, it's quite hard. We had a number of questions on a variety of topics, well, related to the topic about modeling and measurement of this phenomena, these kind of oscillations, power electronics. And I think the takeaway was, although most system operators and owners had some capability to detect and analyze these oscillations, they were all concerned about their capability not being sufficient in future. There's sort of increased risk of inverter-based oscillations in future because there are getting more and more of these renewable energy devices. At the same time, existing monitoring systems are very reliant on sort of manual analysis. Although if you look at the graph on the right-hand side there, sort of how people use their monitoring systems, the majority of utilities were using them in post-event analysis. So having had an event, an experienced event, then digging through the measurement data after the event to understand what happened. And there's very limited use of real-time monitoring, so human operators or feeding into real-time automated systems. So I guess the takeaway was that although we can analyze these events, I think they kind of get swamped if we get more and more events, and we need something cleverer to manage and look at the data. So it kind of supports the aims of the project, really. And yeah, that's me. So next slide, and I think we're back to Jacob for a slide.
Yes, so I'm going to cover quickly, I think, one of the reasons that we've got some opportunities to really address this problem, both through the project and through the wider industry kind of position that we're in at the minute. There's been a lot of kind of work on innovation projects and elsewhere on looking at collecting the kind of data you need to monitor these oscillations. You need high sample rate, high resolution data collected centrally to be able to analyze these events. So the VISOR projects, the previous CIF innovation project, looked at these events and sort of collected that data into a collection system. And as part of the outcomes of that, there's PMU deployments across the UK, both in our network. Scottish Power already have a lot deployed, and National Grid are looking at the same. National Grid then get this as part of the SCCP 27.1, so a new transmission owners code of practice. We need to install these PMUs for visibility. So there is going to be lots of data available from the network to look to address these issues. It's also the case that yes, the IBRs are kind of coming into the network. They don't have the same system stability benefits of a standard synchronous machine, but they have a lot of really useful technical capabilities that can be used to mitigate these events themselves. And they've got very large megavar ranges. They can be designed to have power oscillation damping as part of their control systems, and you can change their control modes on the fly effectively. You know, if you design it such that way you can change those control modes. They are just effectively computer system control modes, so they can be changed. You can't change the properties of your synchronous machine, but you can on your power electronic device. Next slide, please.
Right, hello everyone, Titan Hong here from Strathclyde University. I'm the academic lead from the project from Strathclyde. So in the project, in addition to the survey Fabian mentioned earlier of the stakeholders, we also conduct a survey of real world oscillation events. So basically we look at what happened around the world, and what we found is that Scotland is certainly not alone seeing this phenomenon, and we see many other countries like Australia, US, China, they have seen similar events happening increasingly in the past several years, mainly particularly in the area with high penetration of renewables. And then we look into the details about the fundamental mechanism of this new oscillation and evaluate the existing and also emerging measurement, monitoring, and control solutions. And what we found that is the IBR-driven oscillation, and a unique feature is that a majority of them are caused by the controller design of the IBR units or the control interruption. And the frequency range of the new oscillation can be much wider compared with what we've seen conventionally in the system. And that leads to the existing monitoring device like PMU may not be adequate, and we might need something with higher resolution. And we look at the existing solution as well. Vast majority of them still focusing on relatively lower frequency oscillation. And there are emerging solutions being proposed. However, they're either in R&D stage or they are limited real-time mitigation capability available. So something further are required to address the challenge we are facing right now. Next slide, please. So in order to better understand the phenomenon, and in addition to literature review, we also investigate how we can model, simulate, and replicate those events in our lab or in our platforms in alpha phase. So we look at the high fidelity EMT modeling. We also look at relatively lower fidelity phasor domain. And we also look at how other people around the world has simulate or replicate those events to gain the experience. And then we develop the modeling and simulation requirements for us to pursue in the alpha phase. So what we found is EMT modeling is what we want to proceed because of the wider range of frequency of the oscillation we are targeting. And we also found that ideally we should aim for vendor-specific detailed controller model from manufacturers, even though it could be black box. Although it is possible to use generic model, but it is ideal to use vendor-specific model, given the dependency of the oscillation on the controller design. On the right-hand side, you can see a modeling kind of a plan we come up with from First stage, targeting the oscillation type and area we want to target, to collecting the required data we need, and then on the third stage is developing the real-time model in RTDS simulator, and that is the key stage we are going to pursue in alpha phase. Help us to understand the oscillation better, but also it allows us to further develop it to enable real-time testing of potential insight solutions and beyond beta through hardware in the loop, closed loop testing. And we are going to pursue beyond alpha phase. So that's me. I'll hand it over to, I think it's David or Jakob.
I think it's me again this time. I'm going to quickly run over some of the sort of potential benefits of the project. So I think the key thing with this project is that the benefits of it are kind of the end goal has benefits, but every step along the way, every sort of step we do in terms of further understanding these events in and of itself introduces a lot of benefits to understanding the system, understanding how we can plan it and operate it going forward into the future. If we can deliver a system that does real-time kind of monitoring, alarming and control, it really does improve that system visibility. By doing that, you improve your resilience and reliability of the system. If we can do that, we can provide actions for real-time sort of mitigation of oscillation events. We can respond to sort of real-time system issues, improving the reliability and resilience of the system. And it also then lets us, even if an event hasn't been predicted through the models we've created or in the system planning stages, it allows us to still respond to it. So it gives you that kind of resilience and reliability to unforeseen future events. And what it also does is it uses the sort of inherent capabilities and benefits of IBRs in terms of inverter-based resources, in terms of they can have control modes. Yes, the control interactions is the driver of a lot of these, but you can change them. They can be changed. They're computer software. They can be altered. They can be used, and it's trying to sort of make benefit and use those tools that are coming to help increase the system reliability. Next slide again.
Yeah, back a slide, please. So good afternoon, I'm David Gregory from ESO. I'm a power system engineer and network operability team. So just want to give a few thoughts on how our thinking of the project has evolved. So initially we were looking at allowing real-time control of TO devices to damp oscillations, but there is a broader picture here, so we can start thinking about how you apply it to the GB network. So we talked about use of IBRs, inverter-based resources. So is there scope there to assess users' assets' ability to dampen these oscillations? So you can then sort of start tailoring a response to an event on the system. Can we determine who's the most effective to damping an oscillatory mode, which would be kind of give us a lot more flexibility in terms of system operation. Does raise questions there about, is that the right approach? These sort of types of instabilities are intended to be designed out, so the grid code currently places the onus on users to assess and address those kind of behaviors and mitigate them before connecting. So I mean, it does raise sort of wider questions about, is that the right way forward? But that's kind of where our thinking is on how this project could be taken forward. So move on to the next slide and things back to Jacob.
Yes, so we've talked about kind of what the gaps are in terms of the current approaches, what we need to do going forward. I think I'd like to sort of cover on to what we think we can do in the next alpha phase and where we can go forward in terms of the Insight project. So the Insight project, we're really going to look at what can be done with higher resolution data, using PMUs, using waveform data that's out there, using WMUs, which are even higher resolution versions of PMUs. Look at what real-time control actions can actually be applied using the expertise of the HVDC Centre, and looking to come up with a kind of validation methodology for techniques for both monitoring and alarming for these events, but also then applying those mitigation actions. So I think the key thing we're looking at is how do we create a sort of testbed platform for different solutions that can be used to assess what is the best action to take in the event of one of these things occurring, and how do we prove that that's the right action to take, and how do we test what the approach is to do that? Thank you very much. I think that's all we have from ourselves today, and if you've got any questions, please let us know.
Brilliant. Thank you so much. Thanks, Jacob. Thanks, David, Chitang, and Jonathan for the presentation. Yeah, again, quite a fascinating kind of project, looking at what some of the issues could be in kind of future stability on the power system. So I think I've not seen any questions, but I think we've got a couple of minutes. I've got a couple of questions, if that's okay, just to kick us off, maybe until that time will come. I guess the first one is, you looked at kind of international experience, and I think you did some surveys, etc. Like, what are the key learnings from other countries? Is UK going to be facing some of these issues earlier than some of the other countries? Because I know US, some states particularly have looked at kind of inverter-based resources and impact on power systems. Like, is there any learnings on what they've found and which direction they've kind of gone in terms of potentially either market-based approach or the kind of mandatory requirements on some of these assets to kind of dampen, etc.? Like, any learnings from international experience?
Should I answer this one as I did the survey? So I think internationally, all utilities are experiencing similar type oscillations and problems that they've got to manage as a result of the move to power electronic devices and away from traditional generation. And I think that most people are relying on the traditional approach that sort of David outlined, of talking about trying to get people to do compliance by doing studies up front. But I think that the sort of gap in that is that people still connect things. They think they've sold everything, and then something comes out of the woodwork after something's been designed, and trying to understand it and adapt the control or design of equipment so that it gets fixed. And I think all utilities are using this post-event analysis, where they dig out the measured data from all the devices they can see the oscillation on and try to understand what happened. And it's quite a laborious process. But I think, the state of the art in terms of, Strathclyde looked at the simulation and calculations, but everyone's trying to find ways to solve these problems. And we've got kind of a suite of tools for solving these problems, but trying to do it in a slick, quick way, I think there isn't an easy way. So trying to think of a more clever way forward is kind of where this project goes.
Can I quickly add a comment, please, Mano? So basically, I think what we found is obviously many countries are seeing those events increasingly, and what they have done right now is kind of they see the events, and then as Fabian mentioned, they take out the results, and then they do the analysis and try to analyze what happened, and then try to come up with something. But obviously, there's no kind of systematic solution saying, okay, if something happened in real time, I know what I should do. And the danger there for now is the potential cause of this type of oscillation can be very diverse. And it can get more and more frequently happen, particularly when the system has low demand and a lot of renewable connected. So I think what we are looking for is something more comprehensively understood, tested, and something is more readily or quicker to respond with informed decision making, with confidence as well. I think that is something. I think through the survey with the stakeholders, I think there's general feedback we got. They do have something. Most of them, they say they have something available, but most of them don't feel confident it is adequate. And I believe that is something, and the value that this project can bring to build the gap, basically.
I think maybe time for one more question. I think there's one in the chat. What are the kind of most common root causes of these events?
I think I can take this one. So I can see in the chat I share comment. So depends on different type of oscillation, but what we are focusing on is a new type of oscillation induced by the renewable generation, inverter interface renewable generator. And vast majority of them are caused by the controller design. So different manufacturers, they implement the controller in different ways and tune their controllers in different ways without a good knowledge about what other controller are doing. So for example, you might have a wind farm in one location, and then somewhere you have an HVDC converter nearby. And the manufacturers of these controllers, they don't know what the other controller are doing. So unintentionally or some kind of occasionally that might interrupt undesirably, and that is, I think, more than 50% of the event is caused by the controller interruption, and that is the main root cause. And the issue there is the controller design can be so diverse. So this undesirable interruption could be something we know already, but it's something else, another type of frequency, another range of frequency might observe in the future. So that is something making the issue more challenging.
Got it. Thanks, Chi-Teng, and thanks all. I think we've kind of run out of time, but I think, yeah, it shows the kind of criticality of this, given the amount of renewables we need to install, and really for the transmission operators and others to really understand these oscillations, model, simulate, and almost potentially predict and manage them. So, yeah, thank you so much for the presentation and taking the questions. Really appreciate that. Thanks all.
Thanks, everyone. Thanks, Manu.
Thanks, everyone.
Thank you. Thank you. So moving on to the kind of final project of the day, which essentially, as I was saying, quite fittingly is looking at a black start and looking at novel ways of kind of potentially bring the system back through offshore wind farms. Can I call, I think, who do we have? Kind of Ian, Rob, Mark, and Augusti? Do we have all of them on the line?
Yeah. So I'm Ian McPherson from Scottish Power Energy Networks, and we have Robert Keast from Carbon Trust and Augusti from University of Strathclyde. We have quite a lot of partners on the project, as you can see at the bottom of the slide pack. Obviously, SP Energy Networks are the lead, working with Carbon Trust and University of Strathclyde, as well as SSE as well. Go to the next slide. So the challenges that we face, obviously with renewables and Black Start, or as it's called now, electrical system restoration, there's policies and standards that are being put in place that require us to bring up 24 hours, bring up 60% of the electrical network, and these are the demands put on companies such as SP Energy Networks. We have traditionally been working on Black Start capabilities using distribution assets and creating small islands. And obviously, if you start bringing up your electrical network, that could take quite a lot of time, and it could introduce lots more islands, which you need to maintain. As you bring up multiple islands, you need to also look at how those islands are maintained. Wind could drop, solar may drop as well in power. You may have issues in the case of hydros, of water shortage. So when you bring up islands from a distribution perspective, which is very critical for GB in order to restore power, you've got small islands which you then eventually form into bigger islands, and you form the network. Where we see the benefit of working on offshore wind farm is that you're looking at 1 gigawatt, 2 gigawatt, 3 gigawatt wind farms from a transmission level perspective. So distribution restoration services are from the bottom up, if you want to look at it that way. Transmission is from the top down. So in order to restore services 60% within 24 hours, offshore wind supplies the power and the capability to bring that network up. We still need distribution restart capabilities for certain parts of the network, but we envisage that offshore wind can supply a fundamental ability technically and commercially to actually get up the electrical network and supply power to our consumers in GB quicker and faster. The challenges we face obviously is that offshore wind has its own challenges. How do we get an offshore wind farm to be self-starting? How do we deal with the long electrical cables, the larger inertia issues that we have on the transmission circuits with big power swings? So there's challenges both on the electrical network side as well as on the wind farm side. So this project is to bring together not only the electrical network part of it, the OEM suppliers of the wind turbines, the developers, and basically end-to-end all the assets to understand how we can use and harness the offshore wind. So we have a couple of challenges there. Obviously, part of the National Grid tenders require a certain percentage availability for a service to be put under an SLA. So you may have a 2 gigawatt offshore wind farm, but they may only be able to contract on a 80% basis, 400 megawatts of energy. Now that might be enough energy to supply off that wind farm. But one of the challenges we're looking at is how do we actually bring multiple wind farms together in order to satisfy a higher gigawatt capability to bring the network on. So this project is, again, how do we meet the industrial requirements and commercial business requirements to get our networks up 60% within 24 hours. The other issue is that offshore wind is slightly different to onshore wind in some respects, in that once you've built an offshore wind farm, it's a lot more difficult to retrofit black start capabilities and restoration service capabilities such as grid forming. How do you get the batteries offshore? How do they become self-starting? All those need to be built in many years in advance. So what we're trying to drive here is to try and create a technical standard that all offshore wind farms are built to, so that always have the ability to be grid forming and self-starting. And that requires bringing, as I said, bringing the developers, bringing the OEM suppliers, bringing companies like SSE and Scottish Power Energy Networks together, along with Carbon Trust, who are the OWA representative. How do we bring all that together to create a commercial viable solution for offshore wind to supply and satisfy GB's need on restoration services under black start conditions? So that's the main driver for the project and the challenges we face. Do you want to go to the next slide? Robert?
Thanks, Ian. So just as a quick overview of the consortium, yeah, as Ian mentioned, we've got a powerful consortium of networks, system operator and an advisory role. We've got OEMs or manufacturers, suppliers in an advisory role as well, and 10 offshore wind farm developers. We've said there that the breadth of the consortium is essential, and again, that's getting to the point that Ian mentioned, whereby this is a problem that needs kind of an end-to-end solution. So, you know, right from the companies who manufacture the offshore equipment, the technology suppliers, we've got the offshore wind developers, we've got the onshore networks. We also have offshore network designers of the future. So we've got National HVDC Centre advising around the future offshore network research from Strathclyde, and we have TSO in an advisory role, the National Grid ESO, and I should say as well that we're seeking to add international TSOs to make sure that the learnings from this project are internationally applicable, and making sure that the standards that Ian mentioned will be similar across the globe and taken up across the globe as well. Next slide, please. So just an overview of what we did in Discovery. There was 3 main work packages. Work package 2 was a literature review. You can see the brain there on the left-hand side. All parties in the consortium have done previous work with black start from offshore wind, or at least from wind and offshore. So we did a big knowledge sharing piece to make sure everyone was upskilled on what each of the parties has done in the past. We then did a technical overview of looking at some of the potential black start methodologies that could be used from offshore winds to restore onshore networks. And we also did a preliminary look at a qualitative level around the business case for restoring the onshore networks from offshore wind. So if I hand over to Augusti with the next slide.
Yep, so this is Augusti Gies, senior lecturer at the University of Strathclyde. And mainly here, what I would like to discuss with you a little bit is the technology aspects of the Black Star. And what's interesting about Black Star from offshore wind is that this is a new functionality, and there are, let's say, a lot of implications, not only from the point of view of the market, that's something we'll discuss later on, but also from the point of view of the technology. In fact, we are still discussing how to do it. And what we did in Discovery is we did a literature review. We also had a lot of discussions with wind turbine manufacturers, and we had plenty of discussions with wind farm developers. And basically what we saw is that we have these main 4 different types of ways to do, or technical ways to do the Black Start from offshore wind. And usually they are classified by the aspect where the energy, the initial energy for the first kick comes from to start the wind farm. And basically here what we have is some options that this first energy kick is offshore. For example, we can have an energy storage, for example, sitting into the platform, or even some discussions on the diesel generator that is already existing there, even though it seems that this is small at this point. Also can be self-starting wind turbines. This means that each or a group of wind turbines has an energy storage inside the turbine, and this one is the one that provides the first kick. And later on, if this energy doesn't come from the offshore side, it might come from the onshore. So basically what this means is that we might have a battery nearby, for example, other SIF projects like Incentive, they suggest something similar. So the energy can come from a battery onshore, and later on you energize the cable, and later on the wind farm. Or later on, we can go for hybrid solutions. This is a discovery. And the idea is that what we would like to do moving to alpha is we would like to understand. So basically, we know that Black Star is possible with the standard power stations, but we would like to understand how we can make it possible from offshore wind. So basically, what we are going to do is analyze the needs of the network, and especially the needs of offshore. For example, the export cable, that this is, let's say, a piece of that will provide a lot of technical challenges. But also we would like to identify the onshore wind farm capabilities during Black Star for the scenarios that we have been discussing in Discovery. And this what will allow us is basically identify what requirements, what equipment we need, for example, how this can impact the grid code, how this can impact the business case, but also try to understand what the technology, what control, what comms or protections we need, and especially what kind of models and simulations we need for that. And after that, the idea is once we have identified the bits and pieces that would make this possible, we'd like to go for a more detailed feasible study, and also a demonstration site that basically these days we are already in discussions to try to identify this site. Next slide.
Thanks, Augusti. I think with mind on the clock, I can see we're running out of time a little bit. I might just skip this slide, but needless to say, we've been conducting a business case assessment at a qualitative level. I think the next slide is probably a bit more, if you can move on, a bit more demonstrative of what we've really achieved in the discovery phase. So we've brought all these, I think it's 18 parties in the consortium together to discuss the issues around getting restoration from offshore wind going. And really what discovery phase has confirmed is our suspicion that there's a classic chicken and egg scenario going on that's preventing kind of commercial investment into the technology and rollout into commercial developments of offshore wind. So at the moment, if we start on the top left, TSOs are essentially unclear at the moment as to offshore wind's capabilities of restoring the onshore networks. That means requirements and incentives for offshore wind are unclear to provide these capabilities. So that means developers aren't really pushing the OEMs, the technology suppliers, for the solutions. There's therefore no clear investment case for providing those solutions, or the OEMs kind of investing in the capability. And therefore we have immature, unproven technology, and therefore the TSOs are unclear, and the cycle continues. What we're trying to do in this project really is to stop that cycle in its tracks. And as mentioned, with that really broad consortium, we have the people across the board in the consortium to address each of these issues. So that's the need for the alpha phase. I think I'll hand back to Ian just to give a high-level view of what we're planning. On the next slide. Ian.
Sorry, I was on mute. As Augusti and Robert has said, that we've done a paper exercise. We're now all aligned as a consortium about what do we know, what are the gaps, and how do we need to move it forward. So for the alpha phase, we've broken it into two sort of key chunks: an economic assessment of offshore system restoration, what the costs, to quantify what it's going to cost to retrofit and upgrade a wind farm versus putting it in from the start. What local grid upgrades are, because it's not just about, this project's not just about the wind farm itself, it's about enabling the wind farm to energize our network for up to 50 miles. If we can get the electrical network in, as an example, in Scottish Power's transmission network, energized for 50 miles, we then know that we can build in additional assets within the electrical network, whether that's within SSE or it's within National Grid, in order to supply power across the whole of GB network to get restoration to work. Yeah, so we can harness power from East Anglia, we can harness power from the north of Scotland, and we can harness power, in the case of Scottish Power, off of the East Lothian coast in order to bring up our network in quick succession. So the main work package is looking at it from an offshore wind farm perspective. Technically, there's we need a grid forming, self-starting offshore wind solution, specified and costed up, and that's just what this program will do. Just to point out that not every single turbine needs to be grid forming and self-starting. So we need out of a ratio of the turbines that are deployed offshore, a certain amount of them would need to be capable of self-starting. So the investment doesn't say that every single wind turbine needs to have that capability. It just needs to be enough in order to bring an offshore wind farm energized and ready to then produce and bring in the grid following turbines to then energize the network. So we're looking at the economic assessment and how we can cost effectively deploy this type of capability in a resilient and robust way. So we're focused on one type of wind developer, if you like, to focus on the work package one, that then will drive the economic assessment and show what the economic assessment is for the developer, for the electrical network supplier, what will Ofgem, National Grid, what are the commercial aspects of that, and how can we formalize a commercial business case to allow these developers and turbine OEM suppliers to develop this capability for the GB network. As I said earlier, one of the challenges is we need, it's not like a coal-fired power station. Wind doesn't happen all the time. So it's very difficult for an offshore wind farm supplier for 1 gigawatt capability to sign up to supplying 1 gigawatt of power for Black Start restoration services. The wind then depicts that. So it could be 60% of its capability, it could be 80%, it could be 40%. But a wind farm by itself may only be able to sign up, as an example, to 40%. So this amount of power for 40%. But if we can combine and coordinate offshore wind, and that's a bigger challenge because obviously different developers, how do they combine and coordinate the assets together? So they could sign up to the same power, but for high probability percentage, if you like. So they could say, well, we can supply that power 80–90% of the time as a coordinated set of developers, whereas as an asset by themselves, they couldn't sign up to that. So work package 3 is about trying to take the learnings from work package 1 and work package 2 and work out what it would actually mean to try and get multiple offshore wind farm developers to actually communicate self-start. So you could end up with 2 offshore wind farms being self-starting capable, and then they bring in the other offshore wind farms into that top-up service, if you want to look at it, in order to supply that larger gigawatt capability. So there's some technical commercial aspects in part of work package 3 as well, and how we can do that. The driver then is to do some simulations and modeling as part of Alpha, and that will drive the beta phase, which will include hardware in the loop modeling, and we'll focus in on certain wind farm solutions that are being deployed today. Now, when I say today, the majority of wind farm providers and developers have already...
Ian, sorry to interrupt, but if you can finish up quickly, please.
Okay, I can finish up there then, Manu, yeah. So.
Yeah, that's great. I think you've kind of gone over and then gone over your Q&A time as well. But no, I think it's a fascinating presentation. Thank you so much to you and the team for talking about this. Unfortunately, I don't think we have time for Q&A. So maybe just jumping ahead, we can bring this session to a close. So I think first of all, thanks to all the networks and the project partners for, I know it takes a lot of effort to kind of pull these presentations together and kind of prep for Q&A, etc. So yeah, I really appreciate you taking the time and presenting, and hopefully people who attended it got a lot of kind of useful information about it, and hopefully it's kicked up some kind of questions and potential opportunities for partnerships as well. So thank you so much for all your engagement and preparation for this. If you can move to the next slide, please. Yeah, just to say, if you kind of enjoyed this, please do join the other show and tells. Tomorrow, we're going to be talking about flexible heat networks and also thinking about kind of more distributed heat flexibility. And then on Friday, we're going to talk about cross-vector approaches for transport, and it kind of continues next week as well. Please do kind of sign up and attend these if these areas are of interest, or pass it on to colleagues or friends who might be. And just to say, I think there's one more slide, hopefully, which is, I think, for this round of SIF, we're working with the Carbon Trust to deliver webinars. If you have an idea, but you want to understand a little bit more about the energy system, the policy, the regulatory side, the commercial aspects, and you think you need that information before you can come into SIF, please do register for these. It's open to everyone. It'll be a really good kind of educational series. It'll be a good place to kind of ask questions as well. And so, please do come along and attend these, and do pass it on to others who you think might kind of benefit from it. So I think with that, I think all that's remaining again is to say thank you so much. I really enjoyed the session, and hopefully you found it kind of informative as well. So thank you so much for giving up your morning for us. Take care and see you tomorrow. Bye-bye.